Hello everyone, I am Subhadeep from SketchX Lab. I'll be presenting our paper called How to Handle Sketch-Abstraction in Sketch-Based Image Retrieval. So, freehand human sketches comes in different levels of abstraction based on factors like drawing skill, style, culture, etc. Existing models typically learns the backbone network by triplet clause and extract features to perform retrieval. On the other hand, we learn a novel abstraction identification module to dynamically assess the input abstraction, and we select the appropriate level in the feature embedding matrix to perform retrieval. Moreover, we also develop a differentiable accuracy at Q loss that allows the retrieval metric to accommodate different levels of abstraction. Coming to the baseline FGSBR model, given an input image, baseline FGSBR obtains a d-dimensional L2-normalized feature using a ImageNet Pre-10 PG16 backbone. It trains over triplet loss that aims to minimize the distance of a sketch feature from its paired positive photo feature while increasing that from a random negative one. We hypothesize that a highly abstract early sketch may correspond randomly with multiple plausible photos from the gallery, and as the drawing episode progresses, a sketch should start corresponding to its GT paired photo. Now, entropy being a faithful indicator of randomness, we judge the randomness using entropy of distance in the embedding space for a given query sketch over successive levels of completion. Following our hypothesis, as the sketch approaches completion, the distance between the sketch query and positive photo should ideally decrease, thus decreasing the overall entropy. However, this graph shows that the baseline FGSBR model, being limited by the triplet loss, deviates from our ideal hypothesis and depicts an arbitrary entropy behavior. Accordingly, when we address this in our model, it depicts a constant entropy decrease. To achieve the safe retrieval behavior, we design a few salient design components within our system. Firstly, we introduce the notion of abstraction identification for the first time in context of FGSBR. Secondly, in our design, we adaptively select the number of rows of the feature embedding matrix based on input abstraction level. And thirdly, perhaps the most important design is utilizing a pre-10 style GAN to distill its knowledge into the GSBR system. And last but not the least, we also propose a novel parametric surrogate loss named accuracy at Q that dynamically attends to any level of abstraction. So representing a 256 cross 256 image in style GAN manifold would require 14 unique latent vectors, where the initial 9 latent vectors typically control the image shape and the rest vectors controls the fine-grained appearance. Likewise, sketch being a sparse binary line drawing can only provide structural cues in the context of FGSBR. Thus, during training, we exclusively use the structural related codes. Sketch and photo features generated by the shared ImageNet Pre-10 PG16 backbone, upon passing through the separate feature matrix embedding networks, generates the 9 cross D feature matrix. So continuing on this, depending upon the input abstraction level, we dynamically decide the number of row vectors for the final feature matrix, where the number of rows control the degree of abstraction. Abstraction identification head takes the global average pool sketch feature from the backbone as input and gives a one-hot encoded vector indicating one abstraction level among three: data, coarse, medium, or fine. So identifying abstraction level is a 3-class classification problem that helps to dynamically decide the degree of abstraction of the input sketch, thus dictating the cardinality of effective rows in the feature embedding matrix. Considering the sequential abstract nature of sketches in mind, we render input sketches at 30, 60, and 100% and use them as one-hot encoded ground truth for coarse, mid, and fine level of abstraction. And to distill the knowledge from a pre-10 style GAN, we use sketch to photo and photo to photo reconstruction losses. Upon passing the final feature embedding matrix to a pre-10 style GAN, we compute the reconstruction loss as this equation, and using this reconstruction objective, we aim to align the sketch photo feature embedding matrix to that of the disentangled latent space of a pre-10 style GAN. And coming to the differentiable accuracy at Q loss, unlike triplet loss or other deep metric losses, accuracy at Q directly mimics the FGSBR evolution metric by measuring the percentage of query samples having true match gallery photos in the top Q list. However, measuring accuracy at Q over the entire batch invokes non-differentiability and restricts end-to-end training. To overcome this non-differentiability, we take the help of step function, which we approximate with a temperature-controlled sigmoid function. We use Q as 10, 5, and 1 to model coarse, mid, and fine levels of abstraction respectively. Coming to the result analysis, this table benchmarks the proposed method with baseline and other state-of-the-arts in two datasets, SHU-V2 and GRV2. As seen in the table, the proposed method consistently surpasses other state-of-the-art methods in terms of both accuracy and human study mean opinion score. These are a few qualitative results on SHU-V2 and GRV2, like top 10 results. And this depicts the abstraction method variation. To showcase the abstraction agnostic behavior of the proposed method, we abstracted the input sketches using the GDSA method at different abstraction budgets. This figure shows that how the proposed method reasonably retrieves a ground truth paired photo, even in the case of etching abstraction of 10%. And finally, this figure qualitatively depicts our method's efficacy for over tripletation for the case of different sketch styles, for example, good, reasonable, and abstract for the same object. The proposed method equipped with the dynamic abstraction identification module surpasses SOTA tripletation in every case. Thanks for listening.